fabric known as spacetime, and massive objects like the Sun curve this fabric, causing planets to follow the curvature in their orbits. To observers, this curvature manifests as a Newtonian gravitational pull. Einstein's theory of spacetime has reigned supreme for over a century, overshadowing competing theories. The discovery of gravitational waves in 2015 further cemented its significance. However, like its predecessors, it may soon face challenges as it clashes with another prominent theory in physics, quantum theory. The quantum world is known for its peculiarities, where particles can exist in multiple places simultaneously. In the 1930s, Erwin Schrödinger famously illustrated the strange nature of quantum superposition with his Schrödinger's cat thought experiment. It involved a sealed box containing a vial of poison connected to a hammer triggered by a quantum measurement. According to quantum physics, until the measurement is made, the particle exists in a superposition of both states, leading to the paradoxical scenario where the cat is simultaneously alive and dead. However, this picture of quantum superposition cannot be reconciled with the continuous and smooth fabric of spacetime. Even Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, acknowledges this conflict. According to Einstein's theory of spacetime, a gravitational field cannot be in two places simultaneously, it's influenced by matter and energy and is subject to curvature. However, quantum physics suggests that matter and energy can exist in multiple states simultaneously, defying traditional notions of locality. This raises the question, where does the gravitational field reside? Hossenfelder admits that there's no satisfactory answer to this question, highlighting the current challenge in reconciling general relativity with quantum theory. When attempts are made to merge these two theories, mathematical inconsistencies arise. Calculations sometimes yield probabilities greater than 1 or even infinity, which have no meaningful physical interpretations. Thus, the two theories are mathematically incompatible. Physicists, akin to historical monarchs seeking alliances, are now searching for a unified theory of quantum gravity. This endeavor aims to reconcile the two rival theories and establish harmony between them. String theory is one of the most famous proposals in this quest. Often considered an outlandish possibility, string theory proposes that tiny vibrating strings make up subatomic particles like electrons and quarks. Just as different notes can be produced by placing strings on a musical instrument, string theorists argue that different combinations of strings create various particles. This theory is appealing because it has the potential to reconcile general relativity with quantum physics, at least in theory. However, for this theory to work, the strings must vibrate across 11 dimensions, which is 7 more dimensions than the 4 dimensions in Einstein's spacetime fabric. Currently, there is no experimental evidence to support the existence of these extra dimensions. While it is an intriguing mathematical concept, we cannot be certain if it accurately describes the spacetime in which we live without conducting experiments. According to Jorma Lucke at the University of Nottingham, in response to the perceived shortcomings of string theory, physicists have turned to an alternative approach called loop quantum gravity or LQG. With LQG, the two theories can be reconciled by challenging one of the fundamental principles of general relativity, which posits that spacetime is a continuous smooth fabric. Instead, LQG suggests that spacetime consists of interwoven loops, providing structure at the smallest scale. This can be likened to a length of cloth that appears smooth at first glance but reveals a network of stitches upon closer inspection. Alternatively, it's similar to a photograph on a computer screen that consists of individual pixels when zoomed in. However, the challenge with LQG is that when physicists refer to something being small, they mean it's incredibly minuscule. These defects in spacetime would only be observable at the Planck scale, which is approximately a trillionth of a trillionth of a trillionth of a meter. The number of loops in a cubic centimeter of space would surpass the number of cubic centimeters in the entire observable universe, according to Lucke. Spacetime variations are limited to the Planck scale. It would be challenging to test this theory using any particle accelerator. It would require a particle accelerator approximately 1,000 trillion times more powerful than the Large Hadron Collider, or LHC at CERN, which would need to be as large as our Milky Way galaxy. However, a team of physicists from the UK, France, and Hong Kong may soon have an alternative method to test this idea. They intend to utilize an ultra-cold gas containing billions of cesium atoms existing in a state known as a Bose-Einstein condensate to investigate whether gravity exhibits quantum properties. In the meantime, the universe itself offers another venue to search for small spacetime defects. Light that reaches us from distant parts of the universe has traveled through billions of light-years of spacetime. Although the effect of each spacetime defect would be negligible, interactions with multiple defects could accumulate and potentially yield observable effects over such vast distances. Astronomers have been analyzing light from distant gamma-ray bursts over the past decade to search for evidence supporting loop quantum gravity. These cosmic events occur when massive stars collapse at the end of their lifespan. However, there are unexplained systematic distortions in the spectrum of these distant bursts, as noted by Hosenfelder. It's uncertain whether these distortions occur during their journey or are related to the bursts themselves. The matter is still undecided. To make progress, it might be necessary to go beyond the notion that spacetime is a smooth and continuous fabric, as suggested by Einstein. According to Einstein, spacetime remains in place like a stage, and objects move within it. Even without any celestial bodies, spacetime would still exist. However, physicists Lauren Friedel, Robert Lee, and George Harmonic propose a different perspective. They believe that spacetime does not exist independently of the objects within it. Instead, spacetime is defined by the interactions of objects. This perspective considers spacetime as an artifact of the quantum world itself, rather than something separate from it. While this idea may seem unconventional, Harmonic describes it as a precise approach to the problem. The appeal of the modulus spacetime theory lies in its potential to address a long-standing problem in theoretical physics regarding locality and a phenomenon in quantum physics called entanglement. Physicists can set up a situation where they bring two particles together and link their quantum properties, even when the particles are separated by a large distance. Changing the properties of one particle instantaneously affects the other particle, violating the principles of relativity. Einstein famously referred to this phenomenon as spooky action at a distance. The modulus spacetime theory can accommodate such behavior by redefining the concept of separation. If spacetime emerges from the quantum world, proximity in a quantum sense becomes more fundamental than physical proximity. Minnick explains that different observers would have different notions of locality depending on the context. It's comparable to our relationships with others, where we may feel closer to a loved one who is far away than to a stranger who lives nearby. Hosenfelder adds that these non-local connections are permissible as long as they remain relatively small. Friedel, Lee, and Minnick have been working on their idea for the past 5 years and believe they are gradually making progress. Minnick emphasizes their conservative approach, taking things step by step, but acknowledges the tantalizing and exciting nature of their research. Their novel approach focuses on exploring a quantum world influenced by gravity rather than quantizing gravity itself, as done in loop quantum gravity. Like any scientific theory, it requires testing, and the team is currently working on incorporating it into their model. While this may seem esoteric and only relevant to academics, it has the potential to significantly impact our daily lives. Our existence is intertwined with space and time, and any changes in our understanding of spacetime would not only affect our comprehension of gravity but also quantum theory in general. Hosenfelder explains that all our current devices function thanks to quantum theory, so a better understanding of the quantum structure of spacetime would have implications for future technologies. While these effects may not manifest in the next 50 or even 100 years, they could become apparent within the next 200 years. Hosenfelder uses the metaphor of a monarch nearing the end of their reign and a new successor being overdue. Once we determine the most likely contender among the various theories, a revolution in theoretical physics could ensue. Astronomers, scientists, and physicists are faced with this situation and must consider the best course of action to address these ideas and discoveries. Alongside string theory and loop quantum gravity, several other theoretical frameworks and ideas have been proposed to unravel the mysteries of spacetime and gravity. These alternatives seek to provide fresh perspectives on the fundamental nature of the universe. Some of these theories include causal dynamical triangulation, CDT, emergent gravity, asymptotic safety, quantum graphity, and noncommutative geometry. Causal dynamical triangulation, CDT, offers a quantum gravity approach that represents spacetime as a network of triangles. This theory aims to describe the emergence of space and time through discrete building blocks and focuses on the causal structure of events within spacetime. Emergent gravity is a perspective that challenges the notion of gravity as a fundamental force. Instead, it suggests that gravity emerges as an effective description of more fundamental quantum interactions. The holographic principle, inspired by string theory, is an example of emergent gravity where a lower-dimensional theory can accurately depict a higher-dimensional spacetime. Asymptotic safety proposes that gravity might be a safe quantum field theory at the fundamental level. Unlike conventional expectations that gravity becomes uncontrollable at high energies, this theory suggests that gravity remains well-defined and predictive even at extreme scales. Quantum graphity presents a theoretical framework in which spacetime is represented by a graph with nodes and edges dynamically interacting to give rise to the familiar properties of space and time. This idea explores the possibility of understanding spacetime as a network-like structure. Noncommutative geometry challenges the conventional notion that spacetime coordinates commute at the smallest scales. Instead, this theory suggests that space and time exhibit noncommutative properties, which could lead to a fundamentally different description of the fabric of the universe. While string theory and loop quantum gravity remain prominent contenders in the quest for a unified theory, scientists have diverse perspectives and ideas about the nature of spacetime and gravity. Two notable figures within the scientific community who offer contrasting viewpoints on the matter are Roger Penrose and Michio Kaku. Roger Penrose, a distinguished physicist and mathematician, has made substantial contributions to our understanding of general relativity and black holes. His concept of conformal cyclic cosmology posits that the universe experiences infinite cycles of expansion, with each cycle beginning with a Big Bang and concluding with a Big Crunch. Penrose has also introduced the concept of gravitational collapse as the mechanism behind the formation of black holes, shedding light on the intricate dynamics of these celestial objects. In contrast, Michio Kaku has played a crucial role in the development and popularization of string theory. While acknowledging the significance of string theory, Kaku also recognizes the challenges it faces in terms of experimental verification. He emphasizes the need for technological advancements, such as more powerful particle accelerators, to test the predictions and implications of string theory. Kaku remains open to alternative ideas and approaches, including loop quantum gravity, emergent gravity, and other theories that may offer new insights into the nature of spacetime and gravity. The scientific community thrives on the exchange of ideas and the exploration of diverse theories. As researchers continue to delve into the mysteries of the universe, debates and discussions surrounding the most promising approach to unified general relativity and quantum mechanics persist. Each scientist brings their unique expertise and perspective to the table, contributing to the vibrant landscape of theoretical physics and paving the way for future breakthroughs. So, what are your thoughts now on this matter? Let us know in the comments section, and thanks for watching. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. Well, first of all, it is a Big Bang model. In other words, there is a Big Bang, but the Big Bang was not the beginning. The Big Bang theory proposes that the universe started from nothing, signifying the beginning of the universe. Before the Big Bang there was nothing, no time, no space. But what if I told you that time is an illusion and that the Big Bang theory might be wrong? New findings from the James Webb Space Telescope are questioning the accuracy of this theory. The Big Bang might not mark the start of the universe after all, and there's a possibility that time is just an illusion. Remarkably, this notion finds support from esteemed British physicist Roger Penrose. You might be curious about how the James Webb Space Telescope supports the idea of time being an illusion. Moreover, if the Big Bang theory isn't accurate, what other theories have been suggested to describe how the universe began and developed? Let's delve in to find out. The notion that our universe started expanding over 13.8 billion years ago in a dense state called the Big Bang theory has encountered obstacles, especially with recent images from the James Webb Space Telescope. While these images are captivating to the layman, they have caused concern among cosmologists and astronomers. The surprise felt by experts stems from the fact that these images contradict the Big Bang theory. This theory has long been upheld as true by many scientists, so the new data has caused a significant upheaval in the scientific community. Astronomers like Alison Kirkpatrick from the University of Kansas are troubled by this development, questioning the validity of their previous work. The issue lies in the characteristics of the galaxies depicted in the JWST images. These galaxies appear unusually small, smooth, and surprisingly old according to the Big Bang theory. As space expands, galaxies and other objects should appear larger as they move away from us due to the stretching of light. However, the JWST images show that the galaxies become smaller as the distance increases, which contradicts the theory. Even galaxies with greater mass and brightness than our own Milky Way appear 2 to 3 times smaller in the JWST images compared to previous observations by the Hubble Space Telescope. Additionally, the red shifts observed in these galaxies are also 2 to 3 times greater, further challenging the assumptions of an expanding universe in the Big Bang theory. These facts suggest that distant galaxies must be exceptionally tiny to account for this optical illusion, which is implausible. The presence of these small and smooth galaxies undermines the notion of expansion, thus casting doubt on the Big Bang theory. Supporters of the Big Bang theory were aware that their assumptions required the existence of these small and dense galaxies, often referred to as Mighty Mouse galaxies based on previous observations from the Hubble Space Telescope. However, the JWST images have worsened the situation by refuting the idea that these tiny galaxies could grow into larger galaxies through collisions or expansion. The JWST images show well-formed spiral structures and smooth disks similar to the galaxies we observe today. This contradicts the expectation of mangled and distorted galaxies resulting from collisions. Without significant mergers, the tiny galaxies cannot become 100 times larger, indicating that they were not initially small. This finding challenges the optical illusion predicted by the expanding universe theory, suggesting that there is no expansion and consequently no Big Bang. The age and abundance of galaxies in the JWST images also pose problems for the Big Bang theory. By using infrared filters, the JWST can capture the colors of distant galaxies, allowing astronomers to estimate the age of the stars within them. According to the theory, these far-off galaxies should represent a time around 400 to 500 million years after the Big Bang. However, some of these galaxies show stellar populations that are over 1 billion years old, contradicting the assumption that nothing could have existed before the Big Bang. Moreover, theorists expected that as the JWST peered deeper into space and farther back in time, there would be fewer galaxies and eventually no dark age. However, the images reveal galaxies as large as the Milky Way even just a few 100 million years after the theorized Big Bang. Furthermore, the number of galaxies observed at red shifts above 10 is at least 100,000 times greater than predicted by theorists. It is implausible for so many large galaxies to form in such a short period, challenging the Big Bang theory once again. These findings have led to the questioning of the concept of time itself. Some scientists argue that time is merely a human construct, a way to differentiate between the present and our perception of the past. They propose that time is an illusion created by human memories, suggesting that everything that has ever happened or will ever happen is occurring simultaneously. This perspective challenges the idea that time must move strictly in a forward direction. Some adherents of the Big Crunch theory even suggest that when the universe stops expanding and starts contracting, time may reverse, leading to a reversal of the cooling and expansion observed in the Big Bang. Eventually, the universe would collapse back to the point where it began. The implications of what comes after a big crunch remain uncertain, with various theories proposed. Some speculate that the universe may undergo a fresh start with another Big Bang, while others suggest the universe may simply cease to exist. Certain ideas propose a cyclical nature, with the process repeating multiple times, creating multiple universes. This ongoing debate about the direction of time has prompted scientists to question its fundamental nature. Some argue for a block universe concept where space and time are interconnected in what is known as spacetime. According to a theory supported by Albert Einstein's theory of relativity, time and space are part of a four-dimensional structure where each event has its position in spacetime. This implies that everything, including the past and future, coexists in spacetime, making them equally significant alongside the present. Physicist Max Tegmark from the Massachusetts Institute of Technology aims to address this concept. He suggests that reality can be depicted as either a three-dimensional space where events unfold over time or a four-dimensional,